a quick explanation of this problem, right? So what's the accuracy? So you have how many correct is here and here. So it's 75 out of 100, right? So it's 25%. What's the recall if cat is positive? So there are 40 cats, right? And we got 20 of them, right? So it's 50% recall. All right, the last one. So this startup claims that, oh, it has 85% accuracy. Should we use this model? No. Why? Why? This is more than what we have, right? Yeah, that's true. Yeah. We don't know the training data, or we don't even know what their data set, their test set is, right? Because here it says it's benchmark, right? Not our benchmark. The data can be different. That's one thing, right? So first, the number might not be comparable. Another thing that you might talk about is like maybe we don't care about accuracy, right? Last time we talked about different kind of metrics, right? And there are many kind of metrics. So maybe like in our application, we care more about recall or like precision, right? But so we need more information, right? Something like that. So that's something that you can discuss in this like part. All right. So that's the quiz, right? So very easy, right? So we'll do this every class. It will be a short thing, related to what we did last time, right? All right. A quick recap from last time. So last time we talked about linear regression, which is a model where we have the input features, and multiply by some weights, which can be written as some dot product of vectors, right? And last time we talked about, to train this model, we use the mean square error to compute the loss function, which is just the error, right? Error of the model squared, so that you can average different sides of the error, the positive error, negative error. You can just square it so that you can combine them, right? And last time, like we use this loss function to find zeta, right? And how we find zeta is we do gradient descent, right? Gradient descent, right? So that's from last time, right? We do some we differentiate this loss function, and then we're, here's the gradient, and that's how we can train the model. Now, so this setup, right, is motivated from mean square error, right? In this class, we're going to talk about maximum likelihood and naive Bayes, which is related more about like probabilistic view of machine learning. So this time we're going to look into like probability and how we can estimate probabilistic models, right? And we'll use this tool to help us work on work on like logistic regression, which we left out last time. So this part is more like a quick review of something you probably learned before, which is like parameter estimation. So let's say I have like a coin, which is either head or tail, right? And I want to estimate the probability of a coin landing heads, right? So I say, okay, this coin has a probability of head is theta, and theta is some fixed parameter, right? That is unknown, right? Unknown to us, right? But it's fixed, but unknown, right? And we want to estimate, our goal here is to estimate this theta, right? And what we can do is we can collect data. We can collect data, which is, let's say we toss the coins 5 times, right? And we get this, right? 3 heads and 2 tails, right? So we toss the coin and we get 3 heads, right? So our question is, okay, from this data, what's the best theta that we can use, right? If we have to guess a theta, right, what's the best theta we can guess for? And from our like intuition, we will say, oh, 60%, right? Because the data says so, right? But why is it 60%? Right? So what we can do is we can say, okay, from this data, right, we can calculate the probability of seeing the data that is governed by this fixed unknown parameter, right? So the probability of seeing head, head, tail, tail, head in this setting of like assuming the probability of head is theta. So we say, okay, this probability, right? This probability is theta, theta, 1 minus theta, 1 minus theta, and theta, right? So this is just, okay, to see head, head, tail, tail, head, right? This is the probability. And our goal here, we want to maximize this, maximize the probability of our model to explain the data, right? Which is we want to maximize this probability. So we say, okay, let's try to max this, right? Max this. Right, so we want to find the argmax of theta that maximizes. How can we maximize this? So we can say, okay, this is equal to this, right? And we can differentiate with respect to theta, which will give us, how do we differentiate this? Anyone remember this for the rule, right? Now this one plus this, right? and we set this equal to 0. Okay, and let's try to cancel some things. Here, bam, bam, bam. So we get which is boop, sa- or theta equals to 305. All right, which is what we expect. All right, what we expect that okay, the theta is 305. All right, so yes, this framework of like, okay, setting up the probability, right, as from our model of the distribution with some parameter, we can find the parameter that maximize the probability, right? This technique is called maximum likelihood estimate, the technique that we just did, right? Which is just, okay, we want to maximize, right? This likelihood is just probability here. The likelihood is probability of encountering the data given the parameters, right? And we're estimating the value, right? So this is maximum likelihood estimate. And from this simple technique, we're going to use it in many machine learning models. I think you guys learned this in some class, right? Maybe, I think. Yeah. All right. Let's do another quick one. Gaussians, right? Simple. Let's say you have a data, right? A data set that has like I numbers, right? And we want to estimate. And you say, okay, this data comes from some Gaussian, right? Come from a Gaussian distribution, right? Which some mean, right? And some variance, right? But this one is known. This one you want to estimate, right? Estimate. Right? How do we do, right? How do we do this? Well, from statistics, we say, okay, the mean is just average, right? But why is it the average? We can set it up, right? So we want to find the probability, right? Probability of x1, right? With some of the mean, probability of x2, the mean, probability x3 of the mean, and we want to find the mean. And all of this are Gaussians, right? All of these are Gaussians. Well, for first is we might say that, okay, maximizing this is the same as maximizing the log of this because the log is in monotonic function, right? So if you want to find the argmax, it doesn't change the value of the argmax. The max will change, but the argmax, like the location of the maximum, is the same. When you press the when you add include the log, right? The location of the maximum is the same, but the value of the maximum is different, right? So this still remain the same, right? And if we put in the log, right, this will become a log of px1 plus log px2 plus blah blah blah. Adding the log doesn't change the argmax. This step is usually what people refer to finding maximizing the log likelihood. Log likelihood. Okay, and then we put in the Gaussian distribution, which is, what's the equation of the Gaussian? Is this exponent x minus mean square variance. All right, so this is the equation of the Gaussian, right? Equation of the Gaussian. So we can plug in. If we take the log, right, we get log of 1 this and plus x1 minus mean square plus log of 1 to pi x2 minus mean square theta 2 plus log of 2 pi blah blah blah. Oops, I forgot the negative. There's a negative. Right. You take the log of this, right? Log of multiplication becomes addition, right? Addition. So you get this part, and log of exponent just becomes the inside of the exponent. And we want to find the argmax of mu, right? Find the argmax of mu. So what do we do next? We take the derivative with respect to the mu. This 0, 0, 0. And we get right, something like that. And this is some fixed value. All right. we can also remove this, right? So now we have how many mules? How many mules we have? We have I of them adding together. Right, so we get I mu equals to sum of x j, yeah, j from I to I, j from 1 to I, right? So this becomes just the mean, right? That's the equation of just the mean. Right? So yeah, that's right. Everything looks fine, right? In doing this, maximizing the probability to estimate the parameter of a model, right? So that's some warm up. That's some warm up. Hopefully this is not so new to you. And now we're going to come back to our linear regression. So last time we said, okay, use MSE, right? Mean square error, and then do gradient descent, and we're done, right? That view is not probabilistic at all, right? There's no probabilistic view in there. But let's say that we want to view our model in a probabilistic manner. How would we do it, right? First, we want to think about like, okay, how do we view our linear regression model as a probability, right? We can say, okay, let's assume that we're modeling the world as some model, our model plus some Euler term. What do I mean? We have some model, so this is our model of the world, right? Our linear regression. And we have some Euler term. And this is our ground truth. Right, so this will be our view of the world now. Right. And here we're going to make some assumptions. First, we're going to say, okay, the Euler term, we're going to assume that it's Gaussian. It's a normal distribution with mean 0 and variance, some variance. Right. So first, let's think about this assumption a little bit, right? That is like assuming the error of our model being some Gaussian distribution. Is it like a very restrictive assumption? Is this assumption valid, or is this assumption like bogus and our modeling of the world is strange? Right. Right. The Euler. Do you think like modeling something and our Euler is Gaussian is okay or not okay? Yeah. Yes. So your friends say, oh, Gaussian is very common in nature, in physics, right? When a lot of the distribution in physics and things like that are like Gaussian distributed. In statistics, there's like this theorem called central limit theorem, which says like, oh, a lot of distribution, if you add them together, you'll get a Gaussian distribution. So yeah, it's okay, right? Let's work with that assumption for now, right? And but what about this zero mean? Assuming the error has zero mean, is it okay? can I have like, oh, actually my Euler has a mean of 1? Is it possible? Hmm. If your Euler has a mean of 1, that means like your model is shifted, right? Your model has an Euler of mean 1. What should you do if your Euler has a mean of 1? You should bring the Euler here into your model, right? If you know the mean is 1, right? Oh, you're always off around like by 1 point. You should just put this 1 point into the model, right? And usually in our model, right? In our model is zeta 0 plus zeta 1 x1 plus zeta 2 x2, right? So you have this what we call the bias term, right? The bias term that, oh, if you have a mean of 1 here, you can just put this mean into this bias term and make this 0, right? So a non-zero mean in the error, you can always move it into the model. Okay, so all right, that's our assumption of the model, right? Our error is 0 mean and Gaussian distributed. So what does it mean, right? What does this mean? It means that we can actually infer the distribution of y given x, given the input, the distribution of y. If we know this, right? If we know this, and our model is also fixed, right? This is fixed. This is fixed. What is the distribution of y? Since this is Gaussian, right? Gaussian plus some constant. If you have a Gaussian distribution and you add some constant to it, you get a Gaussian with the mean, right? So here, right, this constant that you add, right? Before this is 0 mean, right? 0 mean, you add some constant. So now this is your new mean of your Gaussian, which is now y, right? So y is still a Gaussian as well with a mean that is shifted, okay? So now with this, we have now the distribution of y, okay? Uh, and now we come to our maximum likelihood setup, which is, okay, we have m data points. We want to maximize the probability. We're going to assume that each data point are independent, right? If they are independent, the data points, each data point will be just multiplying the probability of each data point, right? Because they are independent. Otherwise, you have like, oh, probability of x1, x2, x3, x4, right? Because they are all independent, you get px1, px2, px3, right? You get a multiplicative. So this is our likelihood, right? And we want, since we're taking the argmax, right? We're taking argmax, we can do the same trick of putting the log, right? So we're going to maximize the log, the sum of the log p y I given xi with some parameter zeta. And this right? If we plug in the Gaussian distribution, we will get right, right, taking the log of the Gaussian give you something like this. We just did on like a easy Gaussian before. And we're going to, just like in this thing, we take the mean. I mean, we take the derivative, right? We take the derivative. We take the derivative with respect to theta. We take the derivative with respect to theta. What do we get? So this 0, right? 0. And we have this term, right? We only have, we left with this term. If you notice, right? So what is this term? Is sum, right? Sum of some square thing, right? With some constant, right? Some constant. This form is very similar to MSE, right? So this is MSE, right? Some difference, right? Sum square, right? This is square difference sum, right? So, but this is we want to maximize, right? We want to maximize, but there's a negative here, right? Negative here. So we want to maximize some negative thing in MSE, right? In MSE, we want to minimize some positive thing. So they are equivalent, right? Maximizing something negative is minimizing something positive. You just flip the sign, right? Minimizing become maximizing if you flip the sign, right? So here we just show that maximizing the likelihood or maximizing the probability of our model here that like, okay, this is Gaussian and with zero mean, right? Is the same as minimizing the square error. So we just prove that, oh, MLE and MSE is the same thing. It's the same thing, right? So last time we discussed about like, oh, does it make sense to use MSE, right? What justifies using MSE? And we discussed like, oh, actually it's not, the only thing that is good about MSE is like, if you take the gradient, it's easy to take the gradient compared to like absolute, right? Compared to absolute value. But absolute value, you don't have to care about like outliers. It's better for outliers if you have the absolute, right? So here we found out that, oh, MSE has a nice interpretation, right? If you take the MSE, it's pretty much the same as you assuming you want to model a model that the error of this model is Gaussian, right? It's the same interpretation. So this is just like a justification of like what does it mean to use MSE, I guess, if you want to like interpret it in a probabilistic views. Another thing to note is that, oh, the size of the variance, right? The variance of our assumption here right? We assume that, oh, there's some variance. That variance doesn't matter. It just gets dropped in the different in the maximization process. So this assumption is true regardless of like what you assume to be the variance. But the key assumption for MLE here is the error is normally distributed. Right. So this is a key assumption. If you want to like use mean square error on your linear regression model, right? Assuming like if actually anytime you use like a mean square error on some model, you're pretty much assuming that your error is normally distributed, right? So a good check to check whether, oh, are your like, is my model a good fit or not, is to train some model and then plot the distribution of your error. And if the distribution of your error is not Gaussian, right? That's a good sign that, oh, you might want to try to find like different models or like try to find like techniques to make the error more Gaussian, right? So that it fits your modeling assumption better. And this is a common misunderstanding, right? Usually people, a common misunderstanding is that, oh, if you want to use like linear regression, y has to be normally distributed. This is not true. We have no assumption about y at all. The only assumption we made is about the error itself. Any questions so far or comments? I think this is quite a hard concept to like take in. Cool. Okay. All right. Now let's go to logistic regression. So logistic regression, we say, okay, this is our model, right? We have some linear regression parts, right? Linear regression part, but we pass this to the logistic function, right? So this is the logistic function. We just pass it to, pass the linear regression to a logistic function. And last time we said that, oh, MSE is not a good choice for the loss function, right? So this time in this lecture, we're going to try to use like some probabilistic arguments, just like we did previously, to find how to train the logistic regression model. Okay, so before we prove that, let me show you some very interesting property about the logistic function. So the logistic function, if you take the derivative, right? If you take the derivative, so g here is, let's say g set is the logistic function. Okay. So if you take the derivative of this function, it's the same function times 1 minus the function. Right? It has a very nice form. Okay. All right. So what's our setup of the probability in logistic regression? Just like this page, right? we have to discuss first how do we like model the probability distribution of our setting, right? So in logistic regression, we're going to say that, okay, since we're going to either answer yes or no, right? That's logistic regression, yes or no, binary answer. We have two kind of answer, y equals 1 or y equals 0, right? And according to our model, right, our input and our model, we're going to answer yes with some probability, which is our model, and we're going to answer no with some probability, which is the conjugate 1 minus the probability, since there's only two classes, right? 1 or 0. So this is going to be our probability setup. Writing this in an equation, you have like to separate into two cases, right? Two cases, either 1 or 0. Since it's only 1 and 0, there's a simple trick to try to combine two cases together. So you can combine these two equations into one by this simple trick, right? If y equals 1, what happens? So it will get this, right? And this will be just 0, right? So you only get this, right? If y equals 0, you get what? You get 1 minus h, 1 minus h, right? So this is a nice trick to write the above equation in here. All right, so now that we have this form, let's try to maximize this probability distribution. So this is only one data point, right? One data point. If we have multiple data points, and we take the log, right? So we're going to have the sum of the log from 1 to n of this p y given x theta. And if I take the log of this, and let's put some I here. Take the log of this, I will get right? And we're going to take the derivative with respect to theta, right? To find the model, and our theta is inside this function, right? Inside these functions. So let's take the derivative. So we're going to get y derivative of log. Derivative of log is 1 over the log, right? 1 over the log. And then we do chain rule. We have to take derivative of this thing, right? And also we have to so here, right? So that, and the other one is this. Well, let's be explicit. Right? And H, what is H? H is H is G of this. You take linear regression pass through logistic function. That's your model, right? So H, your model is just linear regression pass through logistic. So let's do, what is this then? This is right? And this thing is here. So we'll get G and if you differentiate this, we did it last time. It's only you get just X, the feature, right? The feature that you're taking derivative with respect to, right? So you're taking like, let's say with respect to J, you get the derivative of J, the J feature, right? The J feature. You can rewrite this a little bit to turn this into, oh, this is h of x, 1 minus h of x, and x feature J. So let me copy. Uh, Copy to another page so that I can sort, so I can have more space. Okay, so let's plug in this thing back into this, right? So here we will get y, oh, there's a sum of y h x 1 minus h x divided by h x x j plus 1 minus y minus h x 1 minus h x divided by 1 minus h x. Okay. And cancel. And then you get, oh, I forgot a term. xj. Forgot a term. So now this is y minus y h x plus negative minus hx plus y hx multiplied by xj. And so in the end, you will get this term. You get this. Which is what we just left at last time. That, oh, this is the derivative of logistic regression, right? Just today we just show that, oh, okay, it's actually derivative, right? Okay. I'll pause a little bit for if like anyone want to jot down. Okay. So who, right? We just show, right, that the logistic regression, right, the update looks very similar to, so this is logistic regression, this is linear regression. They looks very similar, right? But it the delivery, the how like the setup is quite different. It just turned out to be like very similar just by how like how the derivative, like the key here is the derivative of the logistic function, because the derivative of the logistic function is like very special. The math works out very nicely, right? I think there's a question last time, like why why logistic regression use this function form, right? Why not just some function that just click at 0 and 1, right? And so this is one thing, right? The math is very nice. Very nice. And actually, there's a connection. Uh, there's a connection. Uh, some of you might have heard of like cross entropy loss in deep learning, right? You say, oh, that's cross entropy loss. Usually if you write cross entropy loss is y log p y. The label multiplies, this is the label multiplied by the log probability of the model, right? So this is cross entropy equation. What we just did, right? This this no this term here, right? Y log probability 1 minus y log 1 minus probability is the same thing. This is just the binary version of cross entropy where it's only 1 or 0. So this is the binary version of cross entropy. Right. So if you are like curious on like, oh, why does like deep learning use cost entropy for classification problem, what does it mean? It just means that, oh, we want to maximize the probability of the data according to our model, just like this. It's just the class just expands. And this binary cost entropy loss, sometimes people call it the log loss, is a very common loss that people use in machine learning. All right. Any questions so far or comments? Or you want to me go over the the math again? It's also okay or whatever. We're cool. 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 I'm just scared. Don't be scared. Okay. Let's actually let's take a quick break. So we'll come back 25 so that you guys have time to, I don't know, go over what just happened. All right. All right. We'll continue. So the next part is about Bayes decision rule, which is a way to a way that we can use probabilistic model to make decisions. Right. So let's look at a simple example here. So let's say that I want to do a cat or dog classifier. So given X, which is let's say the weight of some animal, I want to classify whether it's a cat or a dog. W1 is a dog. All right, so I'm showing two distribution, P of X given W and P of W given X. So my question is, let's say, oh, I have an animal that the weight is 12. Right? And I want to ask like, oh, okay, which animal is this? If my weight is 12. How would I answer this? So one thing I can do is, okay, I look at 12, right? 12, weight is 12. So from here, I have two possibilities. Right? I can trust this one and say, oh, it's a cat because the probability is higher. Or I can say, oh, from this one, it's a dog because the probability of the dog is higher. The question is, which graph should I use to make my decision? So this one is probability of class given X. The other one is probability of X given class. Mm. So what should we compare between? So here, usually when we want to compare, we want to compare probability of dog, right, given some X equals to 12, right, versus probability of cat, X equal 12. Right, we compare these two, which is this this plot here. So we're actually answering, in this case, we're going to answer W1. Right? Because when we make some decision, right, we're given some information and we compare the probability between different choices. Right? On the other hand, what does this mean? Like probability of X equal 12 given dog. What does this mean? It means that, oh, if it's a dog, right, how likely it is to be have weight 12, right? Which is different from what we're asking, right? That, oh, I have some animal that weight is 12. What should be the animal, right? So in general, when we make a decision or we make some classification choice, right, we compare against the same input, right, of the probability, which is this one. But we can also start with this probability as well. If we have this probability, we can do what? We can do this, right? And this will becomes this according to Bayes rule, right? So ultimately, if we have this one or we have this one, we can always make a decision according to our input data. Okay. So this is a simple decision rule that we can do, right? From the probability distribution of the class that we are concerned with. So our goal, right? So from this, right, our goal that is that, oh, if we can find either this or this, we can always make some decision, right? So let's discuss how we can find either of this distribution. So one way is make a histogram. Right, make a histogram. And we estimate the histogram and then we compare, right? So that's one way. Another way is what we call parametric approach. That is, we're going to assume that, oh, okay, let's assume that this distribution is some distribution with parameter. So let's say, oh, this thing is Gaussian. Right, this thing is Gaussian. Then we can estimate that, oh, okay, what kind of Gaussian is this thing? Right, we get some training data and then we estimate the Gaussian. Right, we can say, okay, this W2 is some Gaussian with some mean, right? Mean 12. Right. This W1 is some Gaussian with some mean. Right. So this is what we call a parametric approach of distribution estimation. On the other hand, histogram, using histogram, we call it a non-parametric approach that we want to estimate the model. Right. And we talked about this before that, oh, if we want to estimate some parameters, right? We can always do maximum likelihood estimate just like this. Right. If we assume some distribution, we can find the estimate for it. Right. So one way to estimate is maximum likelihood estimate. Right. Which is trying to maximize our likelihood, or what we did before is, okay, probability of X with some parameter theta, right? And here, this is just the equation of Bayes rule, right? The equation of Bayes rule. But usually when we talk about this equation, we have special names for each of the term, right? So we usually call this one the likelihood, we call this one the prior, we call this one the evidence, we call this one the posterior, right? This is a standard naming convention, where X is the data and W is the class. So coming back to this simple decision rule, right? First, we find the distribution, like this red line and this black line, and then we make comparison, like, oh, okay, is this one higher? If it's higher, then we say it's class 1, right? So this simple trick of like, okay, comparing distributions is what we call the likelihood ratio test, right? Which is just saying, okay, if probability of W1 given X is higher than W2 given X, we say it's class 1. Right, so this is what we want to do. Right. Usually in practical settings, what happens is in practical settings, we usually start with this. We estimate this distribution. We estimate this X given W. We start with this, and we use Bayes rule to convert to this. All right, so if we go that route of like starting with X given W, usually our comparison, this comparison becomes this Y, right? If we have this P, we have this comparison, right? We can use Bayes rule. And from this comparison, notice how this is the same, right? We can just drop this comparison. So our comparison, and if we just move these two to the other side, right? We get this. This is our comparison that we want to do. So if this term is higher, the left-hand side is higher than the right-hand side, we say if this is true, then answer is W1. And otherwise, we answer W2. Right, so this is the form that we want to compare. We can also like switch side, right? And we get this form, right? That we compare this against this. This is called the likelihood ratio test, because this is just the likelihood term and it's the ratio, right, of the likelihood comparing against the ratio of the priors. The interesting thing about this simple looking criterion of like, okay, let's compare the probabilities, is that this technique this likelihood ratio test minimize classification error. Why is it the case? Let's consider this. There's a distribution P of W given X and a distribution P of W given X on the two class, right? So on this side, we answer W2. On this side, we answer W1, right? If the distribution looks like this, right? So this area is the error because it's class 1, but it's on the W2 side, right? So it's an error, right? This one as well is an error because it's class 2, but it's on W1 side, right? And if you just look, right, proof by looking, that, oh, if we change, if I move this line a little bit, right, my error will increase, right? Because my error is this area add to this area. If I move either way, if I move this green line left or right, my area will increase, right? So from this proof by looking, the likelihood ratio minimize the classification error. Right, this is the best you can do, right, by just comparing the distribution. So this simple technique, right, has many names. So we call it LRT, likelihood ratio test before. Sometimes people call it the Bayes classifier. Just a different name. And there's a different variation. So here, usually in Bayes classifier, we assume that two kind of error. So error type 2 error and type 1 error, they are equally bad. But in settings where they are not, you can add an additional term here, L1 given 2, L2 given 1. What is this? So L1 given 2 means that, oh, actual is 2, but predict 1. The cause, right? The cause of predicting 1 when the actual class is 2. And this L11 means that, oh, the cause of actual is 1 and predict 1. Right? So you can add this cause in the equation, and you're going to compare, you want to minimize the cause of misclassification. For example, let's say that class 1 is, I don't know, predicting someone has cancer. Right? And class 2 is no cancer. Okay. In this case, L1 given 2, which is, oh, someone has cancer, and I say, no, someone has no cancer, and I say he has cancer. I may say, oh, the cause is $10 because he might have some shock, like, oh, I have cancer. And then he went to like have some more exams and things like that to check additional screening, right? But if I answer no cancer, but someone has cancer, the cost might be his life, right? So maybe the cost is this much. Right. So in this case, right, if I have this cost, right, and I plug it into this equation, I will have 10 minus, let's say this one is 0, and 100,000 minus 0. So my ratio here, right, my ratio here, if I multiply it back, right, this ratio here will prefer, what does it prefer? It will prefer that you will answer more on the cancer side. You will answer more on the cancer side because this side, right? This side will have like a an additional 100,000 times. Right? So this is a Bayes loss or risk classifier. Usually, in machine learning, a typical model that people will set up, they will use what we call a 0-1 loss classifier. That is, different class error is the same, right? But in actual use cases, this is usually not true, and we have to deal with this part. Another variant of LRT is called the maximum likelihood criterion. So before we compare this part with this priors, right? But this in maximum likelihood criterion, we compare this term with this term with 1. Right? This is equivalent to, instead of using this form, right? Comparing this form, you're comparing just this, the likelihood equation, or you're treating the prior terms to be the same. That is, you don't care about like how likely a class supposed to happen. All right, so this is the likelihood ratio test. Right, we're comparing the two probability. This is called the Bayes classifier. Right. So in this probability, right, this x here, right, can be a multi-dimensional vector. So let's say that, oh, this x here is a vector and it has m features. Right. So I'm calculating the probability of like x1, x2, x3, x4, xm given w1. So this probability distribution is very high dimensional. It's very high dimensional. So this is very hard. This is very hard. So people have to do additional things with this thing. But before we go there, let's look at some example first. So let's say I have this data set, right? Eight data point, and I'm trying to predict PM 2.5. according to the wind. Right. So my goal is predicting the PM level given the wind condition in the morning. Right. So I want to do this. How do I do this? Right. So I will estimate, right? Estimate the probabilities that are related to this input data, right? So Py given X, right? In this case, right? Since we have like calm and windy, low, medium, high, right? It's a two-dimensional table that we just estimate all the probabilities here, right? We just doing counts, right? There are three calm winds, right? And one of them is low, right? Low PM, so it's 1/3. One of them is medium. One of them is high, right? So you can just count, right? Count the numbers. So that's the maximum likelihood estimate of the probability distribution. So that's fine, right? After you do this, right? After you did this, let's say that, oh, I have a COM, a new input data come in that, oh, okay, this morning there's no wind, right? There's no wind. What should my answer be? What's the PM situation for this afternoon if my wind is calm? Well, it's tied actually, right? All of them is tied, right? So I can answer any one of them, right? Because they're all 1/3, right? But that's the like an example of how you can do like uh uh likelihood ratio case, which is just okay, estimate the probability and then compare, right? Compare, find the maximum. The problem starts when you start having more dimensions. So let's say now I want to predict the PM in the evening. So I want to predict Z, right? My input is the wind in the morning and PM in the afternoon. So if I want to estimate this distribution, I estimate this distribution, my table is a lot larger, right? My table is a lot larger. Now I have how many combination? So this is 2, 3, 3. So all the combinations here is 18 combination, right? But I only have 9 data points. I only have 9 data points. So I can put in all the counts for my 9 data points, right? But I have less data point than all combinations. So some of my table here will have 0 probability. Right. So this is the problem, right? This is called curse of dimensionality. That is when I have a lot of when I have high dimensional data and I want to estimate some probability estimates. I cannot estimate because I will have so many zeros in my distribution. So what do I do? Right? What do I do? So what naive Bayes do, right? Naive Bayes propose a solution for this. That is, oh, if my distribution is very high dimensional, especially in the X, right? In the input data, my input data is very high dimensional. I'm going to assume that, oh, this distribution can be split into a product of smaller pieces. Right. So this assumption is called we're going to do conditional independence. Conditional independence assumption. That is, oh, given the class, the X are independent of each other. That's why they can be expanded into products of each other. So in this case, I have this P of Y given X, P of Y X given Z, assuming conditional independence. This can be expanded into two parts. And now my distribution looks like this and this. So I have how many slots I have? This is 9 slots. This is 6 slots. So I use only 15 slots that I need to estimate. I estimate 15 slots instead of this 18 slots that I have earlier. So by breaking down the problem into smaller pieces, I require less parameters for my estimation. But still, even if we break down the problem into smaller pieces here, since we only have like 9 data points, right? And this is 15 data point, you still get some zero probability. So there are many ways that people deal with zero probability in like real life. So one technique people do is use a very small value. Let's say, oh, instead of 0, I say, okay, this is 10 to the negative 7, like very small value probability instead of 0. Or use smoothing technique that is like, oh, let's say this is a count of 1 here, a count 1 here. I'm going to take some count from here to put somewhere else, like smooth the counts. Take some count from 1, turn this count into like 0.9 and put this 0.1 to the other point, to the other part. Or use what we call map adaptation, which is a Bayesian technique, right? We won't go over this technique. I talk a little bit about this in the lecture notes, which is optional. This part is optional, but if you want to read more about it, feel free to read about it in the lecture notes. So in summary, we just talk about a model called naive Bayes. Naive Bayes. So naive Bayes is just a Bayes classifier, which just compare probability of two distribution, like class 1, class 2, which one is higher, and you pick that one, right? A very simple thing, right? That's the Bayes classifier. From the Bayes classifier, you make some assumption. So this is the Bayes classifier. You make some assumption to break down the probability into smaller pieces, right? And this simplifying assumption makes your calculation easier and lets you work with smaller data, right? So in the homework, if you want to play around with this, right? In the homework, let's look at the homework. So the homework will give you some data set. Actually, I forgot to upload the data set. Let me just go back a little bit. Homework 2. Homework 2. Homework 2. So homework 2 give you some data set that looks like this. So this is a attrition prediction data set that is you're going to predict whether an employee in a company is going to quit or not. Right. So this is for HR, right? HR has to track like, oh, is this person unhappy? Right. If he's unhappy, HR might want to talk with that person and maybe like discuss a little bit like, oh, improving his benefits or like improving his salary and things like that, so that that person won't switch to a different company. Right. So this is like the HR want to know, right? So the data set is just like past data of that company that, oh, this person has some attributes, and whether he will attrition, yes, that means he will leave. No means he won't leave. Okay. And the data set has like, oh, the age of the person, whether that person business travel or not, right? Travel rarely, frequently, the department, right? The department, whether his home is far from the office, the education, right? Satisfaction of the person, and notice missing values, right? There are some missing value in the data, right? Missing value in the data, right? Your goal is to predict this column from this data set. Right. Wait, let me open. So homework 2, right, is the start is like simple Bayes classifier, has some no, this is a spatial data set. Yes. Just to make it harder. Huh? Well, you can just download, right? I upload this in my Crossview later on, but I forgot. But yeah, we take this from Kaggle, but we made it harder by just removing some values. To show you the power of naive Bayes. actually. So why did we remove some features? Well, it's very common in real life that you encounter missing values, right? What do you usually do if you have missing values? Yeah, you can do imputation, or you can drop the data, drop the column, drop the row, right? Or you can impute. How do you usually impute? Mean, right? Median. Actually, those are bad. Please don't do mean or median imputation. My best advice when you have missing values is use techniques. For example, like nearest neighbor imputation, or use models that you don't have to impute. Use model that can handle missing features. For example, XGBoost, or like random forest usually has some mechanic to deal with missing values by itself. Right. Another example is naive Bayes. So what is naive Bayes again? So let's say we want to compare, right? We want to compare probability of X, let's say age given leaf times distance given leaf. We compare it against p leaf, compare against pH stay, p distance c. I don't have space. Oops. And p stay. Right, so this is naive Bayes. You're comparing the probability of two sides. Which one is higher? Let's say, oh, I compute this one is 0.19. This one is 0.05. Right? Then your answer is leave, right, for that person. Right? So this is naive Bayes. When you have missing values, let's say I don't have an age feature, what do you do? You just, if I don't have age feature, I just ignore this term, right? And then I can proceed everything the same way, right? So naive Bayes is a very special kind of model that has like a self-baked mechanic to handle missing value. You don't have to impute. If you have missing value, you just don't compute anything. Don't compute anything. Right. So this is very nice. Right. And in this case, actually, you have to implement your own naive Bayes. If you just use like sklearn, it will force you to impute. But if you you implement your own, you can implement this mechanic, right? So it's a nice motivation on like why you have to implement your own model, which is not hard, and you will do this in the homework. right? So naive Bayes can handle missing data, right? That's the good part. And it's also very fast and quite good in practice. So you can, like, for example, you can look at this discussion on Reddit that talk about like, oh, naive Bayes is like very popular in NLP, things like that. Another important thing that we haven't discussed is about threshold selection. So naive Bayes, what we're pretty much doing is doing this ratio and compare it against 1. Right? If it's larger than 1, we answer W1. If it's lower than 1, we answer W2. Can we use a different ratio, a different threshold for prediction? Right. So this is about threshold setting, right? How do we set thresholds? So let's discuss this concept called ROC. Right. So threshold plays a important part in modeling. Right. So let's say that I have this logistic regression task, right? Predicting whether, so this is my ground truth, and this is my logistic regression model prediction, right? It predicts some number between 0 and 1, right? So usually you have some threshold, right? The default is 0.5, and this prediction is compared against the threshold, right? So here it might be, so I predict, this is predict yes, predict no, predict yes, predict no, predict no, right? According to the threshold of 0.5, right? And after I do prediction, right, I can compute whether it's true positive, false negative, false alarm, blah, 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 right? And compute this metrics, right? Compute the metrics. So I compute the metrics. That's the metric value for a single threshold. I think a single threshold. If I change the threshold, let's say, oh, now change my threshold to 0.15, what happens? So here I will predict yes, predict yes, predict yes, predict yes, predict no. Right? My prediction change. Right? And since my prediction change, my metrics will also change. Right? So my threshold is where has a big effect on the performance of my model. Right? So if you compare, right, compare different thresholds and the metrics, right? Usually, if my threshold go down, my threshold go down, the true positive will go up, the false alarm will go up, right? And the precision usually will go down, the recall will go up. Okay, so this is usually the direction that what will happen when you decrease the threshold. Since different threshold will give you different numbers, right? So one way for people to summarize the performance of a model is through what we call the ROC curve, or stand for receiver operating characteristic curve. How this curve is constructed is that, you pick a threshold. Let's say, threshold is 0.5, and you compute two positive rates. You compute false alarm rate. Let's say, this is 0.6, this is 0.7. So you compute some threshold and you mark it, right? Mark it that, this is 0.6 and this is 0.7. Mark it 1 point. And then you say, okay, let's change. Let's change the threshold. The threshold now is 0.4. And you compute the two positive. Let's say, now it's 6.5 and this is 7.5. So you get another point. Right, you get another point at a different threshold. So as you change the threshold, you get 1 point in this figure. And after you get enough point, you kind of draw some line. You draw some line. And this line is called the ROC curve. So this line is called ROC curve. And this represents a trade-off between true positive and false alarm. If you want more true positive, you're going to have higher false alarm. You cannot have it both ways. That is, I want better true positive. I will have to suffer in the false alarm. And so this curve represents some trade-off. And this is actually the best way to compare different models. If you have two models, it means you have two curves, right? So this blue line is model 1. This red line is model 2, right? A model is a curve. The model is no longer just one single number, it's a curve, right? And when you want to compare models, you actually have to look at the curve. So in this case, which model is better? Model 1 is better because at the same false alarm rate, it has better true positive, right? You want this to be high, you want this to be low. At the same false alarm rate, at the same true positive rate, it has lower false alarm, right? So in this case, model 1 is always preferred. But this is an ideal case. Most of the time, what you will actually encounter when you build models is a curve like this, right? A curve like this. That's not like always like, at every point, right? Every point, sometimes blue is better. At certain point, red is better, right? So this is usually what will happen, right? Especially when your model starts to be competitive. So in this case, right, it really depends on where you want to use your model, right? In the first class, we talk about like Google search, right? In Google search, we say, in Google search, we want high precision, right? When we Google search return something, you want to like, this is correct, right? You want Google search, like when you return something, it has to be correct. It doesn't have to like find everything, right? It doesn't have to find anything, but when it returns some correct results, right? So we want a high true positive we want low false alarm. We want low false alarm. So we want something here for Google search. So in this case, we prefer rule model, right? So this is what you should think about when you're comparing models. Like look at the ROC, consider like, oh, in my use case, what's the scenario I will use, right? So that's a rough idea. But let's dig deep down a little bit, right? If I want to pick where I want to use my model, right? I can be more specific than like, oh, a rough idea that, oh, I want something in this region, right? I can be more specific. How to be more specific? So that's where our discussion about where is it? Discussion about creating some costs for different types of error, right? Different types of error has different costs. We can start thinking about costs and errors. So the simplest one says that, oh, okay, a cost of like miss that is given 0, given positive class, it answer 0. This is a miss. And false alarm is given is positive, it's a negative, you answer positive, right? If these two errors are the same in terms of the cost, this means that the false alarm is the same as, so this 1 minus 2 positive rate is a miss rate. These are equal, right? Or in this plot, this TPR is Y, right? If FAR is X, right? So this has to be true, which means it's this line, right? X equal 1 minus Y, right? This line is just means that, oh, this is the line where number of miss equals number of false alarm. This is the line where they are equal, and the intersection between the ROC and this line means that, oh, this is where model makes equal mistakes in both ways, right? And this is where you can select the threshold, right? This is where you can select the threshold. This is called equal error rate. Right? This is for the case where the error is equally bad. A miss or a false alarm, they are equally bad. If they are not equally bad, for example, oh, a miss is 1,000 times more costly than a false alarm. For example, cancer detection. Right? Cancer detection. A miss is, 1,000 times more costly. You don't want to miss a cancer prediction, right? If this is true, right, we want the false alarm to be 1,000 times more. That is like, if you want to compare the false alarm is 1,000 times the miss rate, right? Which is this line or this line here, right? And this is where we will select the threshold here. ratio. Right, notice how this point is where we have high to positive rate, and we can accept more false alarms, right, in this cancer detection task. Let's look at a more like a real working example, just so that you get some more intuition. Let's say I work at a company. Let's say that I work at AIS, right? AIS, and I'm managing like the subscription plan for the telephone, right? Subscription plan for telephone. And my goal is to predict whether a customer is planning to switch from AIS to True, right? Before the customer attempts to switch, I will call him and offer like a discount so that he doesn't switch before he even talk to me, right? So I want to predict churn. In business, churn means like, oh, the customer is switching provider, things like that. Right. So in this case, let's say that class 1 positive class is switching, right? And 0 means the customer is staying. Okay. And let's look at some monetary settings, right? So let's assume that the fee, the subscription fee for this telephone plan is 50 baht, right? And if I call the customer to offer this this promotion, it will cost me 5 baht just for the operator, right? The operator cost is 5 baht, and I will offer him a promotion, right? A promotion. So this promotion, the fee is 25 baht, right? So now the question is like, can you help me derive a strategy to pick the threshold in this setting? Right. So how do we do this? Well, to start, we need to think about the cost, right? The cost of errors. What is the cost of the customer is switching, but my model say he's staying? What is the cost? Hmm? 50, right? Because I'm losing his subscription, right? What about the other way around? The customer is actually staying, but I predict a switch. You lose 30, right? Because, well, you first lose 5 from the call, right? And you lose this difference, right? You lose the difference. Before, the customer will be paying 50, but now he's paying 25, right? So the cost here is 30. All right, so this is the cost, right? How do we pick the threshold? According to this cost structure. So this is cause of miss, and this is cause of false alarm. Now, according to this, should I have more miss or should I have more false alarm? I should have more false alarm because it's cheaper, right? So, well, coming back to like the previous slide, I need some false alarm rates and like 1 minus 2 positive rates, which is this is the miss and this is the false alarm, right? So what should I put in front of these two? So it's 50, 30. So this has to be true. Or in other words, the line will be 30 divided by 50, x equals y, 1 minus y. It has, so it's a line that looks something like this, maybe, probably something like that. So it's all more on the true positive side because the false alarm is cheaper. Right, so that's an example of how you would work through like in a real setting. You should like figure out like, okay, what's the cost of different choices, right? And then use those costs, cost analysis to strategize how you pick the threshold, right? And this looks very hard in practice, actually, even though this looks simple in practice. Let's say I have cancer screening, right? Cancer screening application, right? What's the cost of a miss and what's the cost of a false alarm? How do we get that? Insurance company, how much do they pay? That's a good one, actually. Uh, a miss usually will end up as a lawsuit, right? So you can look at the coverage of like, oh, what's a typical lawsuit cost? And the miss one is the harder one to price. The false alarm is easier. The false alarm is just the cost of like so the patient will have to go through like additional screening, right? So that's just the cost, right? He has to do additional screening. But yeah, like in general, actually, there's like a big like uh, a field of study in economics that discuss like how do we put price on things. uh, Price of a life, price of like some policy and things like that. So if you're like run into situations where you have to like think about this course and you want to come up with like, how do we come up with some course, right? You can consult like some economists. Usually they will have you some answer for you. And nowadays, I think AI, consulting AI, asking their opinion about this a little bit can give you some rough idea as well. They're pretty good on this kind of things. So that's some tips on like actual practice. Another possibility instead of cost analysis, sometimes you get some requirements as like regulations. For example, like there may be a regulation that, oh, okay, you cannot have more than this amount of false alarm per year, right? Let's say, oh, to pass the standard for this tool, you cannot have more than this, right? So that's just aligned, right? In the threshold selection. And besides the ROC, there's another curve called detection error trade-off curve, which looks like this. So instead of plotting like, so ROC plots TPR and false alarm, right? That plots miss rate, which equals to 1 minus TPR. So it's just a flip up down. Another curve is precision recall curve, PR curve, which plots between precision and recall. But I think for threshold selection, most of the time people will use ROC. Other things that people might use is the area under the curve. I usually don't recommend this as a metric at all. Not recommend, because it hides a lot of things, right? Because like I said before, right, when you actually comparing model, you should think about where you want to use your model. Like, oh, I'm using the model in this zone or in this zone, right? If you compute the entire area, it can be quite misleading, right? So I usually don't recommend, but in academic papers with no clear application in mind, you will see this metric used, but it's not good practice. All right. So to summarize, in this lecture, right, we talk about the probabilistic view, right, of machine learning, right? When we want to turn our models into probabilities distribution, and when we turn it to that, right, we discuss about how we can estimate the parameters of the model in the maximum likelihood manner, right? Try to maximize the probability in the data, right? When we estimate the distribution, we can use that distribution to do decisions, which is the likelihood ratio test, right? Using the distribution we estimate, we can start doing decision comparing, right? And when we compare things, we can actually think further into the cost, right? Cost analysis to pick the best threshold, right? For the model, right? So that's the main theme of this lecture, right? And if you have any questions, feel free, right? This is all we have for today. And next time we'll talk about unsupervised learning, clustering, and things like that. All right, and that's all.